Hi everybody, this is our test 2 review for Physics 32-3 for fall 2021. So, logistics. Please do write legibly and write your work in a nice linear logical fashion. If I can't read it or can't follow it, it's very difficult to grade. Now, I'm not asking you to show every single step of your math, but bear in mind that a lot of you probably would benefit from some partial credit, and the more work that you show, the more partial credit I can give if you make a mistake. If you just give me an answer with a box around it, I mean, for all I know, you just really like that number. So make sure that you show that. Don't forget your units. If you don't show work, points will be deducted even if your answer is correct, okay? If your answer doesn't have the right units or notation, points will be deducted for that. You'll be allowed a piece of paper as an equation sheet. Like last time, I'm going to give you the fundamental constants. I'm going to allow you a regular size sheet of paper for your equation sheet this time, since we're covering a lot more material on this test. You should bring a calculator and your scratch paper. No phones, laptops, or tablets will be allowed. What we're covering in the test is Chapter 2, Chapter 3, and the first 3 sections in Chapter 4. We're not covering anything else in Chapter 4 at all, so we're good to go there. All right, so launching into the material. First of all, we defined macrostates, microstates, and multiplicities. So a macrostate is a general statement of the condition of a system, like giving the pressure, volume, and temperature for an ideal gas, for example, or saying what kind of hand you have in poker. That's all macrostates. Microstates are the number of ways that you can configure the individual components of a system that result in a given macrostate. So, for example, for the macrostate a royal flush, you could have ace, king, queen, jack, and 10 of hearts, and that's one microstate. The multiplicity is the number of different microstates that go into making the same macrostate. So we use the symbol omega, the Greek letter omega, to symbolize the multiplicity of a given macrostate. Now there's different ways to calculate probabilities and multiplicities. So remember that when you calculate a probability for a system, you do the multiplicity of the system of interest, like the number of ways that you can get a royal flush, for example, divided by the total multiplicity, and that will give you the probability of a given state of the system. You can also calculate the multiplicity for different systems using some of the formulas that we've developed. One of them is the combinatorial function, and that's shown here. Omega is equal to n factorial over little n factorial times n minus little n factorial. All right, so this is for coin flipping or a paramagnet. The multiplicity for that was calculated in that way. Now remember that for that two-state paramagnet, we talked about spin-up and spin-down particles. Spin-up is when the magnetic moment was aligned with the field, and spin-down was when it was anti-parallel to the field. And if there's a total of n total particles, then you would have n would be equal to the number up plus the number down. So the multiplicity for the paramagnet could be given as n factorial over n up factorial times n down factorial. Now, speaking of the two-state paramagnet, just to remind you, if you have a paramagnetic material, then each atom has its own magnetic dipole moment we symbolize with mu. And that's going to tend to align parallel to an externally applied magnetic field B. So there's a torque, mu cross B, that's exerted on that dipole in the field that causes it to rotate. Now, if this is true for all magnets, right? Like compasses, magnets, large-scale magnets in an external field, all that good stuff. And then there's a potential energy associated with that, and that U is equal to minus mu dot B. And that means that if it's aligned with the field, then you'll have a negative potential energy. And if it's anti-parallel with the field, you'll have a positive potential energy. Okay? Now, quantum mechanics tells us that individual atoms have a discretized value for that potential energy, right? So in the two-state paramagnet, there's only 2 possible orientations that we call spin up and spin down. But of course, in a more complex system, which is usually the norm, there's multiple energy levels there, okay? we just dealt with the two-state paramagnet. Remember that that dipole moment isn't perfectly aligned with the field because of the uncertainty principle, but it's aligned at some angle with the field, okay? Now, another system that we covered was the Einstein solid. So, Einstein modeled a solid lattice as a lot of little balls connected by springs as shown in this cartoon. And in this, of course, the springs are supposed to be the bonds, symbolize the bonds in between the atoms. Now, in a three-dimensional solid, that means the atoms can vibrate in three independent directions. Each spring we visualize as a quantum harmonic oscillator. The potential energy for a spring is 1/2 kx squared, and if you solve Schrodinger's equation for that potential, then you'll see that it has energy levels of n plus 1/2 times hf, where n is a quantum number that starts at 0 and goes up in integer steps from there. And that means that the neighboring energy levels are hf apart, because you'd have 1/2 hf, 3/2 hf, 5/2 hf for your energy levels, and the spacing in between those is hf. Now, in thermodynamics, we talk about the number of springs or bonds or oscillators, and those we symbolize with an N, and then we have energy units Q, and that's really just how many excited states that you have. So if you have 3 oscillators with 2 excited states, then you could distribute the excited states in different ways. So for example, if you have just one excited state, then it could be 001, 010, or 100. If you have 2, then it could be distributed in these ways, 002, 020, 200, or you could have those 2 excited states distributed between 2 different oscillators, like this 110, 101, and 011. So that multiplicity, you can see, a max of 2 excited states would be 9 for that system. Now, if you have a specific number of oscillators and excited states, then the multiplicity for an Einstein solid is shown here. Omega is equal to q plus n minus 1 factorial divided by q factorial divided by n minus 1 factorial. And that'll give you the multiplicity of an Einstein solid. Okay, now one of the interesting things is letting systems interact. So if you put, for example, 2 Einstein solids in thermal contact and wait for them to come to equilibrium, they're eventually going to come to the same temperature. And what that means is that the hotter solid has given energy to the colder solid, and it won't happen the other way spontaneously. You can force it to happen the other way, but you have to do work to get that to happen. And this is really just a statement of the probabilities. It's not a fundamental law of nature. It's just that that state, that transfer, has a higher multiplicity than the other possible outcome. Okay, so this is the statement of the second law of thermodynamics. The spontaneous flow of energy stops when a system is at or near its most likely macrostate, which is the macrostate with the greatest multiplicity. All right. Now, in thermodynamics, reasonable systems are huge because we're talking about something that has moles and moles of constituents to it. And then if you talk about the number of ways that those moles and moles of constituents could be arranged, you're getting into very large number territory. So we usually break it down into 3 types of numbers: small numbers, large numbers, and very large numbers. Large numbers are like moles, and then very large numbers are moles to the power of moles, or moles factorial. Okay, so those are very large numbers. And that's what we're usually dealing with multiplicities of systems. Okay, now a couple of ways that we deal with those large numbers are to use logarithms, and you should know the rules for logarithms. All right, they're pictured over here, and be able to work with those rules for the logarithms. Another thing that we often do to get around large numbers is to use approximations, and one of the approximations we like to use is Stirling's approximation. Those are shown here. Stirling's approximation says that n factorial is approximately equal to n to the power of n, e to the minus n, square root of 2 pi n. And then we also often use the log of n factorial because, of course, we have multiplicities, and those multiplicity formulas have factorials in them. And so we end up using this approximation. The log of n factorial is approximately equal to n log n minus n. So you should be aware of those and be able to apply those in problems. Now, we use these approximations on Einstein solids and two-state paramagnets to find the multiplicity of these systems when the number of constituents was a very large number. So for an Einstein solid, we had two approximations that we went over in class and that you did for homework. And one of them was called the high temperature situation, where Q was a lot bigger than N. And in that case, our multiplicity turned into this simple expression here. Omega is approximately equal to EQ over N to the N. And then for an Einstein solid in the low temperature approximation, we had omega was equal to En over Q to the Q. So those were the two approximations that we had. Now, we talked about the sharpness of the multiplicity function of an interacting system. The deal is here that if you let the two systems interact, then the deviation away from the systems coming to thermal equilibrium where the temperatures are the same, right? The deviations away from that are so tiny that basically this multiplicity function looks like a delta function. And we spent a couple of classes talking about this. So the multiplicity function of two interacting solids, Einstein solids, is very sharp. We described it as a Gaussian, if you remember. And then we explained that the full width half max of that function is super, super skinny compared to the scale of the graph. And that for systems of reasonable size, which means, of course, moles and moles of substance, the measurable fluctuations away from the most likely macro state never occur. And that is thermodynamic limit. We also talked about the multiplicity for an ideal gas. I'm not going to ask you to recreate the derivations, okay? And I'm not going to ask you to memorize the function, but just be able to use this equation. You might want to scrawl this equation down, or the Sackur Tetrode equation down on your sheet. And here we have omega is equal to some function of n times the volume to the n power times the internal energy U to the 3n over 2 power. And we talked about applying this in a couple of situations, and one of them was the sort of ubiquitous problem of, does all the gas in a room spontaneously move to 1/2 or stuff like that. Okay, now we defined a whole bunch of multiplicity functions, and so since those multiplicities are very large numbers, what we do usually is talk about them in terms of their entropies. And so the entropy S is equal to Boltzmann's constant K times the natural log of the multiplicity. Now, Boltzmann's constant is a tiny little number, 1.38 times 10 to the minus 23 joules per Kelvin. And then the multiplicity is a very large number. So if you take the natural log of the multiplicity and then multiply it by a little number, then all of a sudden you're dealing with reasonable sized numbers for your entropy. Now, the second law of thermodynamics, we could state it in several ways. We did, in fact. And here's some of the ways. Any large system in equilibrium will be found in the macro state with the greatest multiplicity. An equivalent statement, any large system in equilibrium will be found in the macro state with the greatest entropy. An equivalent statement, multiplicity or entropy, either one, tends to increase in all processes. Okay? And this is for the universe. A mathematical way to state the second law of thermodynamics would be to say that the change in entropy of the universe, which is going to be equal to the change in entropy of the system plus the change in entropy of the surroundings, is greater than or equal to 0 for any process. Okay? Now, the equal to part is for a reversible process. A reversible process has no change in the entropy of the universe. But real processes are generally irreversible. And so that means that for any real process, the change in entropy of the universe will be positive. Okay? Okay, so we then found the entropy of different systems by just plugging into the formula S is equal to K times the natural log of omega. All right? So for example, an Einstein solid in the hot case, omega is EQ over N to the N. We plug that in, and we end up with the formula S is equal to NK times the natural log of Q over N plus 1. Okay, so this is one application of what we did in this chapter. We also introduced the entropy of a monatomic ideal gas. This is the Sackur Tetrode equation. And here, S is equal to NK times the natural log of V over N times 4 pi mu over 3NH squared to the 3/2 power, and then plus 5/2. Okay? So this is the full formula. We're going to derive this formula in a later chapter. We only derived the hand-wavy version earlier. Okay? Here, V is the volume, N is the number of particles, K is Boltzmann's constant, M is the mass of a single particle in this formula, okay? So this is the atomic mass here, not the molar mass, right? And you know it's the atomic mass, not the molar mass, because look there, there's big N. N is the number of particles, not the number of moles, okay? U is the internal energy. H is Planck's constant, okay? So that's what all those things are. Anytime you have big N and little k, you're going to assume that any mass that's in that formula is an atomic or molecular mass. If you had little n and big R, then you would have a molar mass. So please don't make that mistake, okay? All right, now we talked about the entropy of mixing two different gases together, and we're dealing with ideal gases whose molecules are indistinguishable and keeping the pressure constant. And then we said it was as if the volumes of the gases expanded, and so this is how we found the change in entropy for mixing, okay? Nk times the natural log of the initial to the final volume ratio. We talked about the entropy of black holes, okay? So we studied 4 systems: ideal gases, paramagnets, Einstein solids, and black holes. So black hole is here the last one, and then remember that we did that in-class problem to derive the black hole's entropy. I'm not going to ask you to recreate the derivation, but you should be able to use the formula and understand it. Okay, so here, the entropy of a black hole is 8 pi squared kg m squared over hc. Here, k is Boltzmann's constant, g is the universal gravitational constant, 6.673 times 10 to the minus 11 in SI units. M is the mass of the black hole, h is Planck's constant, and c is the speed of light. Okay, that was it for Chapter 2. Moving on to Chapter 3, we talked about first the fundamental definition of temperature. And it's important to remember that temperature is the construct, and it's the entropy that's the fundamental quantity, not the temperature. So temperature, remember, we defined in Chapter 1 as what becomes the same when objects come to thermal equilibrium. And it's used in the measure of the internal energy of the object. It's not the same as the internal energy of an object, remember. So the most fundamental definition of temperature is as it relates to the entropy. So here it is, partial S with respect to U, holding N and V constant, is equal to 1 over T. Okay, now we talked about different kinds of entropy versus internal energy graphs. Here we see one at right. This is S on the vertical axis and U on the horizontal. This is a normal system because it's concave down, as you can see. What happens in most normal systems, like Einstein solids, ideal gases, the entropy increases as the internal energy increases. And as the internal energy gets very large, the positive slope of the graph gets less steep. And these systems have a positive constant heat capacity and positive temperatures, and they behave according to our intuition, okay? But we also talked about abnormal systems, and this is a plot of an abnormal system. This is a black hole. This was called a greedy system, right? What happens is they still have a positive slope, so that means they have positive temperatures, so we're good on that. But the slope gets more and more steep as the energy gets larger. And so what that means is that they have larger gains in entropy at higher internal energy values than at smaller internal energy values, which is different from normal systems. Now these things have negative heat capacities, and that's not so intuitive, because it means that the system gets colder as more energy is added. Remember that as a black hole grows, its temperature goes down, and it gets more and more greedy the bigger it gets. Okay, paramagnets. This was the completely strange one, okay? This is a plot of the internal energy on the horizontal axis versus the entropy here on the vertical axis for a paramagnet. So what we see here is that if you look at the right-hand side of this graph, it has a negative slope. But remember that partial S with respect to U is equal to 1 over the temperature. So if we have a negative slope, then that means, ta-da-da, we have a negative temperature, okay? And this is not negative Celsius, this is negative Kelvin, okay? And remember what we covered in class is that negative temperatures are actually hotter than positive temperatures. If you go with the definition that a hot system wants to give up its energy quite badly, remember that what that means, what this is a paramagnet, right? So it's a magnetic, whole bunch of little magnetic moments in an external magnetic field. The internal energy is higher, right, when the paramagnets are anti-parallel to the field. So these are ones that are anti-parallel to the field, but they feel a torque. that wants to align them with that external magnetic field. So they want to be over here, okay? They want to be over here. Now, these things have positive heat capacities, but they have heat capacities that are not constant. Remember that, for example, a monatomic ideal gas has a heat capacity, a constant volume of 3/2 R. So that's a constant value. Black holes and paramagnets have non-constant heat capacities. Black holes have negative heat capacities, but paramagnets have positive heat capacities. So speaking of heat capacity, we deal with this a lot. Please try and remember the definition of a heat capacity, which was defined in other chapters as well. But for systems that we can determine the entropy function, like ideal gases, Einstein solids, things like that, we can then get the heat capacity by finding the multiplicity function, using the multiplicity to find the entropy, differentiating the entropy with respect to the internal energy to find the temperature, and then using that relationship to find the internal energy function with respect to temperature. We did this, right, for these systems. But we did it for all 4 of these systems. But you don't have to do that, okay? If you have the heat capacity, if you can measure the heat capacity experimentally, then you can use the heat capacity to find the change in entropy. And that's kind of a more straightforward way of doing it when you have an experimental system in your lab. So here's the definition of the heat capacity. This is maybe one of those formulae that you should stick in your head and memorize, okay? So here it is. The heat capacity at constant volume is the partial of the internal energy with respect to temperature, holding the volume and number of particles constant. Okay, so for an Einstein solid, U is equal to NKT and CV is equal to NK. For a monatomic ideal gas, U is equal to 3/2 NKT and CV is equal to 3/2 NK, right? So these are your heat capacities at constant volume, and this is pretty standard. And also, it means that since you have these positive constant heat capacities, you've got a very straightforward way for calculating how much adding a certain amount of heat will change the temperature of a substance. Now, you can also measure the heat capacity of a system experimentally and then use that to calculate an entropy. In that case, your change in entropy of the system, delta S, will be equal to the integral over the temperature of the heat capacity dt divided by the temperature. And of course, that gives you mc times the natural log of T final over T initial. This is the formula that you would use for solids and liquids, mc. Now, if you have a gas, for example, then you would multiply, instead of the mass, the number of moles times the molar specific heat. But then the len T final over T initial would be the same. Okay? Now, if you have something that's going through a phase change, then the formula for delta S would be equal to Q over T, where here we have the latent heat for Q, and then that means that Q is plus or minus ml over T. Remember, it's plus if you're going, for example, like anything that you have to heat up, boiling, evaporating, stuff like that. That's a plus ml, and then freezing or condensing would be a minus ml, and then you divide by the temperature. It's very important for these formulae that your temperature be in Kelvin, because you're dividing by these things, by these temperatures, dividing. And so that means that Kelvin is the way to go. Okay, the third law of thermodynamics. So this is stating that as a system approaches 0 Kelvin, the system should settle into its unique lowest energy state. And at that unique state, the multiplicity is 1, and so that would mean that the entropy approaches 0. And this is one way of stating the third law of thermodynamics. But, of course, real systems, real materials, they have defects, and those defects create residual entropy even at 0 Kelvin. And so sometimes you'll see the third law stated as the entropy of a perfect crystal of a pure substance approaches 0 as the temperature approaches 0. Another equivalent way of stating the third law of thermodynamics is that the heat capacity has to approach 0 as the temperature approaches 0. And the reason for that is this expression right here, right? Delta S is equal to the integral of CV dt over T. So if the heat capacity does not approach 0 as the temperature approaches 0, this expression blows up, okay? So that's a way, then, of stating it. And we showed that this was true, actually, for a bunch of systems. We plotted the heat capacity as a function of temperature for experimentally measured systems, and you can see that, indeed, experimentally, the heat capacity does approach 0 as the temperature approaches 0. And this is because some of the energy states get frozen out as the system cools down. All right, so we also talked about the ways that other functions relate to the entropy instead of just the temperature. So we talked about how increasing volume increases entropy too. So when systems are in mechanical equilibrium, right, a change in volume would be a change in the mechanics of the system. And so when systems are in mechanical equilibrium, their pressures become equal. So remember, we had thermal equilibrium, the temperature becomes equal. Mechanical equilibrium, the pressures equalize, all right? Now, the relationship through entropy for this is that the pressure divided by the temperature is going to equal to partial S with respect to the volume holding U and N constant, okay? Another thing that can change the entropy is the number of particles. If you increase the number of particles, the entropy increases. As we saw, a lot of our entropy functions were proportional to Nk, where N was the number of particles and K was Boltzmann's constant, okay? Now, the way that that's written out is that when systems are in what's called diffusive equilibrium, the thing that becomes the same is that their chemical potential is the same. And remember that what we were allowing to vary is we set two systems, we allowed them to exchange particles. And when they stopped exchanging particles in a net way, then that was when we said the chemical potential was the same. The chemical potential is defined here. Mu is equal to the negative temperature times partial S with respect to N, holding U and V constant. Okay, so you could also write this as minus mu over T is equal to partial S with respect to N, holding U and V constant. Remember that the chemical potential is a negative number by definition, and so particles will tend to move towards lower value of the chemical potential to establish equilibrium. We found then used the chemical potential of an ideal gas. The formula for that is here. Mu is equal to minus kT times the natural log of V over N times 2 pi m f kt over 3h squared to the 3 halves. Remember that f here is the number of degrees of freedom. Okay, so for an ideal gas that's monatomic, that would be 3. For a diatomic, it would be 5. Okay. All right, now if we combined all these expressions for the entropy into one expression, and then we rearranged it, we get the thermodynamic identity. Yet again, this is one of those equations that you should memorize, tattoo on your brain for this class. Here it is. du is equal to TdS minus PdV plus mu dN. Okay. Now, if you have more than one type of molecule, then you can sum over the chemical potentials and number of molecules for all of those, and it would look like this. This led us to talk about the partial pressure for each type of gas. Basically, a partial pressure is just the fraction of molecules in the substance that have that type times the total pressure. So, for example, P total would then be equal to the sum. Here, Ni is the number of moles of a specific type of gas divided by the total number of moles, and then you multiply that times the total pressure. So, for example, air that you breathe is mostly oxygen and nitrogen, and so the partial pressure of nitrogen, since nitrogen makes up about 80% of the gas that you're breathing, it would be 80% of 1 atmosphere would be nitrogen. That would be the partial pressure of nitrogen. And 20% of 1 atmosphere would be the partial pressure of oxygen, roughly. Okay? All right, so that was chapter 3. Now, chapter 4, we talked about engines and refrigerators. So a heat engine is a device that takes energy in by heat and operates in a cycle, and then a fraction of that input energy that they take in, the Q sub H, gets expelled by work, and then the rest is waste heat, Q sub C. Okay, here's a little schematic of that engine here. You can talk about what the efficiency of your engine is, and that's always what you get over what you give. So the efficiency E is the work that the engine does. That's what you get, divided by what you give, which is the heat energy that it takes to get the whole thing to go. Now, since energy is conserved, right, then you have the QH is equal to W plus Q sub C, right, because the energy initially taken in, QH, is dumped into the work and the waste heat. So, using energy conservation, you can write that the work of the engine is QH minus Q sub C. These are all absolute values here, okay? So then that gives you another expression for the efficiency of the engine that dodges the work. So that's 1 minus QC over QH. Now remember that for a cycle of an engine, if you start and end at the same point in the process, your change in the internal energy is 0, and that's the heat plus the work. And so that means that the net heat is equal to the work done by the engine, okay? And that's what it's saying here. Work of engine equals QH minus QC. So another way, yet another way, of stating the second law of thermodynamics is that it's impossible to construct a heat engine that produces no effect other than the input of energy by heat from a reservoir and the performance of an equal amount of work. A less lengthy way of saying that is that there's no perfect engines, and so that means that the efficiency of an engine can never be 100%. You're always going to have some waste heat. We also talked about a heat pump or a refrigerator. It's basically an engine working in reverse, okay? So this isn't going to be your natural direction of energy transfer. So what you have to do is have some power or, some external work coming in, right? So you're reversing the direction of all your arrows. And then what will result from that input of energy is that you will transfer energy, heat energy, in the way that you don't normally transfer it, which is, specifically, you suck energy out of the cold reservoir. Q sub C comes out of the cold reservoir. It makes the hot reservoir hotter, okay? So this is what a heat pump does to heat your home in the winter. It takes heat from the outside and puts it inside your house to make your house warmer. Or alternatively, if you use it as a refrigerator, it's taking the cold box inside your refrigerator, sucking out more heat to make the air inside your refrigerator and the stuff inside your refrigerator even colder, and then it dumps the waste heat into the room, okay? If you're running it in reverse, we instead use coefficients of performance instead of efficiencies to characterize how it's doing. So it's still going to be what you get over what you give though, okay? So if you're using it in cooling mode, like an air conditioner or refrigerator, what you get is the heat sucked out, right? So that's QC divided by what you give, which is the energy that you had to input the work. So it's QC over W is the COP for cooling mode. Heating mode, it's still what you get over what you give. What you're interested in now, though, is the heat energy that you're getting out. You want to know how much heat energy you're creating in that room. So that's QH divided by W. All right, we talked about Carnot engines, which is an ideal engine. It's a heat engine that operates in an ideal reversible cycle, which is called the Carnot cycle. And it's operating between two reservoirs. Now, if you know the temperatures of those two reservoirs, the hot reservoir and the cold reservoir, labeled TC and TH, and those temperatures should be given in Kelvin, by the way, then what it does is it sets an upper limit on the efficiencies of all other engines. All real engines are going to be less efficient than a Carnot engine because they don't operate through a reversible cycle, and so there's going to be more waste. So the formula for the efficiency of a Carnot engine, E is equal to 1 minus TC over TH. Yet again, very important these be in Kelvin. Theoretically, you can run a Carnot cycle in reverse to make a perfect heat pump or refrigerator. And if you do that, then you can find the formula for the COP for the cooling or the heating mode. And the formula for the cooling mode, COPC, would be TC divided by TH minus TC. That would be the coefficient of performance for cooling mode. For heating mode, COPH would be TH over TH minus TC. Okay? That sets upper limits. We also talked about real engines. The one I'm going to highlight here for the last slide in our review is the Otto Cycle. And in this one, you see the PV diagram of the Otto Cycle at right. Okay? So basically, it's 2 adiabatic and 2 isovolumetric processes. So this Otto Cycle, of course, isn't quite a real internal combustion engine, but it's as close as it gets to a cycle that describes the internal combustion engine. So if you want to find the efficiency for an Otto Cycle engine, then the efficiency is given here. E is equal to 1 minus V2 over V1 to the gamma minus 1 power. Gamma is the ratio of the molar specific heats. And we defined gamma 2 for adiabatic processes. It's the same gamma. V1 over V2 is called the compression ratio. And of course you can see here that V1 is greater than V2. So this is the most and least compressed, or the biggest and smallest volumes that your pistons can hold. Okay? All right. Well, that is kind of a tobacco auctioneer review. Remember that in these reviews, I'm not necessarily being exhaustive here. I'm just hitting the highlights to make sure that you can do well on the test. What you'll really need to do is work problems. Go back over the homeworks, make sure you understand the homeworks. Go back over the practice tests that I've posted and make sure that you can do those. Let me know if you have any questions, and I'll see you in class.